All right, so number 1 off the growth and decay worksheet. The pie is removed from an oven at 450 and left to cool at a room temperature of 70. After 30 minutes, the pie's temperature is 200. How many minutes after being removed from the oven will the temperature of the pie be 100? All right, a lot of stuff going on here. I think I'll start with a table of values. We used U for temperature yesterday. I don't know where U came from, except it's not T, so it's better than T. So at T equals 0, the pie was 450 degrees. The room temp was 70. After 30 minutes, the pie's temperature is 200. How many minutes after being removed from the oven will the temperature be 100? So who knows is the first question. This is Newton's law of cooling, and it would give you, anytime you would need Newton's law of cooling, we would give you the formula to use for that. So I may need to find this worksheet and tweak that a little bit, because we would give you that formula. We might only give it to you in this form so that you have to be the one that does the integration to come up with, du dt, to come up with the formula. So integrate both sides. Natural log of u minus 70 equals kt plus c. Absolute value bars are probably not necessary because the temperature is always going to be bigger than 70 as it cools down and approaches 70. So if you dropped them, it would be fine. Let's do the loop-de-loop thing. E to the kt plus c equals u minus 70. So we do a couple of algebra tricks here. I'm going to move the 70 over. I'm going to relocate that c, although it's a different c. C e to the kt plus 70. We have, so there's two things we don't know. We don't know c, and we don't know k. And our usual is plug in the 2 points and figure out what the two pieces are. And usually plugging in the first point tells us what C is. So as e to the 0 is 1, subtract 70 from both sides, so C equals 380. So U equals 380. E to the kt plus 70. So we got C. Now we need to find K, which we can usually find with that second piece of information. So we plug in 200 for the temperature, 30 for the time, and then we'll move things around and figure out what K is. So subtract 70, divide by 380. What do we do next? Next step's a key step. Natural log, that way the 30K goes down. I'm going to reduce by 100, so or by 10, I guess. Natural log of 13 over 38 equals 30K. Natural log of E, which goes away. So K equals natural log 13 over 38, all divided by 30. So now we know what K is. Like, I don't know the number for it, but I've got it defined. Natural log 13 over 38, all divided by 30. So you can write it down if you want to. I would be careful writing it down because you don't want to use 0.036. You want to use the full thing. So store it as K. And now we've got, we would say the problem is defined. Like we know everything there is to know. Like we're ready to work anything they want us to find. Now it's just an algebra problem. It's not a calculus issue anymore. So back to the question. If the temperature is 100, when did it get there? So 100 equals 380 e to the kt plus 70. Except that now we know what k is, so this isn't an unknown k. Like we have k. It's an unknown t. So subtract 70, divide by 380. This is very similar to what we just did, because k and t are in the same spot, so solving for one of them is just like solving for the other one. Natural log both sides. So t equals natural log of 3 over 38 divided by k. We've defined k. K's in our calculator, or it's right there. So natural log 3/38 divided by k is 71.011 minutes. And let's see if that kind of makes sense with our table. So the temperature got cut in half-ish in 30 minutes, and then another 40 minutes it got cut in half again-ish, close. So that makes sense. Like, you can't fully check it that way, but if I'd gotten 32 minutes, I'd be suspicious. Anything less than 30, I would definitely be worried. And if if I got 5,000 or something weird, then I'd be really curious what was going on. So, when you lay them out in a table of values, it gives you a chance to see that your answer at least sort of makes sense.